Hi, welcome back. I'm very excited about this lecture. We are going to make our first OpenGL application. In this lecture, I will focus on one main point, that is developing our first OpenGL application to render triangle, implementing the OpenGL graphics pipeline. The very first step of the graphics pipeline is the input of the vertex data. To start drawing something, we have first to give OpenGL some input vertex data. OpenGL is a 3D graphics library, so all the coordinates that we specify in OpenGL are in 3D with X, Y, and Z coordinates. OpenGL doesn't simply transform all your 3D coordinates to 2D pixel on your screen. OpenGL only processes 3D coordinates when they are in a very specific range, a range between -1 and +1 on all the three axes, X, Y, and Z. All the coordinates within this range, the so-called normalized device coordinates range, will end up visible on our screen. All coordinates outside this region won't be visible. Because we want to render a single triangle, we want to specify a total of 3 vertices, with each vertex having a 3D position. We define them in a normalized device coordinates in a float array between -1 and +1. Even though we have this vertex data, OpenGL cannot use it directly. OpenGL has some limitation on what memory it can read from. You can allocate vertex data all you want yourself. OpenGL cannot directly see any of your memory. Therefore, the first step is to allocate some memory that OpenGL can see and fill that memory with our data. This is done with something called a buffer object. A buffer object is a linear array of memory managed and allocated by OpenGL at the behest of the user. The content of this memory is controlled by the user, but the user has only indirect control over it. Think of a buffer object as an array of GPU memory. The GPU can read this memory quickly, so storing data in it has performance advantages. We create the buffer object with the GL gen buffer, storing the handle to the object in the global variable VBO, vertex buffer object. Although the object now exists, it does not own any memory yet. That is because we have not allocated any with this object. The GL bind buffer function binds the newly created buffer object to the GL_array_buffer binding target. Later commands that affect to the buffer bound to GL array buffer will affect this particular object until a new buffer object is bound to the GL array buffer. The GL buffer data function performs 2 operations. First, it allocates memory for the buffer currently bound to GL array buffer, which is the one we just created and bound. Second, it copies data from our memory array into the buffer object. GL buffer data is a function specifically targeted to copy user-defined data into the currently bound buffer. Its first argument is the type of the buffer we want to copy data into, the vertex buffer object currently bound to the GL array buffer target. The second argument specifies the size of data in bytes we want to pass to the buffer. The third parameter is the actual data we want to send. The 4 parameters specify how we want the graphics card to manage the given data. This can take 3 forms. First, with the GL static draw, the data will most likely not change at all or very rarely. Second, with GL dynamic draw, the data is likely to change a lot. Third, with GL stream draw, the data will change every time it is drawn. In our case, the position data of our triangle does not change and stays the same for every render call. So its usage type should be GL static draw. If, for instance, one would have a buffer with data that is likely to change frequently, a usage of a type GL dynamic draw or GL stream draw ensures the graphics card will place the data in memory that allows for faster writes. This is all what we need to get the vertex data in the GPU memory. But buffer objects are not formatted. As far as OpenGL is concerned, all we did was just allocate a buffer object and fill it with the random binary data. We now need to do something that tells OpenGL that there is vertex data in this buffer object and what form that vertex data takes. GL vertex attrib pointer, despite having the word pointer in it, does not deal with the pointers. Instead, it deals with buffer objects. When rendering, OpenGL pulls vertex data from array stored in buffer object. What we need to tell OpenGL is what format our vertex array data in the buffer object is stored in. That is, we need to tell OpenGL how to interpret the array of data stored in the buffer. In our case, our data is formatted as follows. First, our position data is stored in 32-bit floating point values using the C and C++ type float. Second, each position is composed of 3 of these values. Third, there is a stripe between each set of 3 values that is 3 times the size in bytes of the float type. Fourth, the first value in our array of data is at the beginning of the buffer object. The GL vertex attrib pointer function tells OpenGL all of this. GL enable vertex attrib array activates the vertex attributes. Now an unusual step. Most meshes of objects in a scene will use a collection of one or more vertex buffer objects. In all the OpenGL implementation, we have to bind each of one and define their memory layout every time that we draw the mesh. We have now a new thing called the vertex array object VAO, which remembers all the vertex buffers that you want to use and the memory layout of each one. A vertex array object, VAO, can be bound just like a vertex buffer object, and any subsequent vertex attribute calls from that point on will be stored inside the VAO. This has the advantage that when configuring vertex attribute pointers, you only have to make those calls once, and whenever we want to draw the object, we can just bind the corresponding VAO. This makes switching between different vertex data and attributes configuration as easy as binding a different VAO. All the states we just set is stored inside the VAO. To use a VAO, all you have to do is to bind the VAO using GL bind vertex array. From that point on, we should bind or configure the corresponding VBO and attributes pointers, and then unbind the VAO for later usage. As soon as we want to draw an object, we simply bind the VAO with the preferred settings before the drawings the object, and that's it. Now that our data is on the GPU, we want to call the vertex shader for making the first computation on the GPU. Vertex shaders, as the name implies, operates on vertices. Specifically, each invocation of a vertex shader operates on a single vertex. This shader must output among any other user-defined outputs. Shaders in OpenGL are written in OpenGL shading language GLSL. This language looks like C, but is not much like C. This is what our simple vertex shader looks like. The first line states the version of GLSL used by this shader. In our case, the shader is 3.30. A version declaration is required for all the GLSL shaders. The next line defines an input to the vertex shader. The input is a variable named position and is of type vec3, a three-dimensional vector of floating point values. It also has a layout location of 0. We'll explain a little bit about this later. As we see, a shader execution starts with the main function. This shader is very simple. It's copying the input position to something called gl_position that is vect4, so we need to cast it. gl_position is a variable that is not defined in the shader, because this is a standard variable defined in every vertex shader. Shaders have inputs and outputs. Think of these like function parameters or function return values. If the shader is a function, then it's called with input values and is expected to return a number of output values. When rendering starts, vertex data in a buffer object is read based on a setup work done by GL vertex attrib pointer. This function, as we saw, describes where the data for an attribute comes from. The connection between a particular call to GL vertex attrib pointer and the string name of an input value to a vertex shader is somehow complicated. Each input to a vertex shader has an index location called attribute index. The layout location part assigns the attribute index of 0 to position. In the code, when referring to attributes, they are always referred to the attribute index. We assign the attribute index of the position attribute to 0 in the vertex shader. So the call to GL enable vertex attribute array 0 enables the attribute index for the position attribute. We wrote the source code for the vertex shader stored in a C string, but in order for OpenGL to use the shader, he has to dynamically compile it at runtime from its source code. The first thing we need to do is to create a shader object, again referenced by an ID. So we store the vertex shader as a GLUint and create the shader with GLCreateShader. We provide the type of shader we want to create as an argument to GLCreateShader. Since we are creating a vertex shader, we pass in GL vertex shader. Next, we attach the shader source code to the shader object and compile the shader. The GL shader source function takes the shader object to compile to as its first argument. The second argument specifies how many strings we are passing as a source code, which is only 1. The third parameter is the actual source code of the vertex shader, and we can leave it as a third parameter to null. After the vertex shader, we focus on the fragment shader that processes each individual fragment and output the final color. The fragment shader is the second and final shader we are going to create for rendering a triangle. The fragment shader is all about calculating the color output of our pixels. To keep things simple, the fragment shader will always output an origin color. The fragment shader only requires one output variable, and that is a vector of size 4 that defines the final color output that we should calculate ourselves. We can declare output values with the out keyword that we will here promptly name frag color. Next, we simply assign a vec4 to the color output as an orange color with an alpha value of 1.0, where 1 is completely opaque. The process for compiling a fragment shader is similar to the vertex shader, although this time we use the GL fragment shader constant as a shader type. Both the shaders are now compiled, and the only thing to do is to link both shader objects into a shader program that we can use for rendering. A shader program object is the final linked version of multiple shaders combined. To use the recently compiled shaders, we have to link them to a shader program object, and then activate this shader program when rendering objects. The activated shader program's shaders will be used when we issue render calls. When linking the shaders into a program, it links the outputs of each shader to the inputs of the next shader. This is also where we will get linking errors if our outputs and inputs do not match. The GLCreateProgram function creates a program and returns the ID reference to the newly created program object. OpenGL can now take these three vertices and can convert it into a series of fragments. In order to do this, however, OpenGL must decide what the list of the vertices represents. OpenGL can interpret a list of vertices in a variety of different ways. The way OpenGL interprets vertex list is given by the draw command. The GL_triangles tells OpenGL that every three vertices of the list should be used to build a triangle. Since we pass only three vertices, we get one triangle. If we render 6 vertices, then we will get 2 triangles. We are now ready to put everything together. In this code, I'm using GLFW for the window management and creation. The code is available on Canvas, and let's see how I can compile it and run it on my Mac. Let's look at quickly the overall code. First_triangle.cpp. So we include GLAD, GLFW. We set the screen's size, and here are the two most important things. So here we have the source code for our shaders that are stored as a toString. So here we have our vertex shader source code as a string, and here we have our second fragment shader source code. We initialize our Windows system. We initialize GLAD We compile the shaders. We get some information info if the compilation is okay. We link the two shaders in a shader program, and we get our shader program. After that, we can delete the two individual shaders. This is the input of our vertices. We create first a vertex array object, and then we create a vertex buffer object with the vertices of our triangle. We do the binding, and here our render loop. We use our shader program, and then we draw our triangles and do the swapping of the buffers. We compile it and we run it. Wow, our first triangle. We reached the end of this lecture. So in summary, we developed our first OpenGL application to render triangle, implementing few parts of the OpenGL graphics pipeline. It was not easy, so I think we can congratulate ourselves. In the next lecture, we will write an efficient OpenGL code to display a rectangle. Talk to you in a bit.